This matters because space weather is not just an astronomy topic. Strong solar flares can affect satellites, radio signals, and some systems we use on Earth every day. So when researchers find a better way to spot higher risk activity on the sun, that has practical value right away. The new result comes from a NASA report on long-lived active regions, which are patches on the sun with strong magnetic fields. These regions can appear fast and then fade over, very different to temescals. Some decay in days. Some last for weeks or even months. The new study says the long-lived group seems to produce far more flares than shorter-lived regions, and they are much more likely to be linked to the most intense kinds of flares. That gives forecasters a sharper question to ask, not just what is active now, but what has stayed active for a long time. The key finding is specific. Researchers looking at long-lived active regions found it produced disproportionately more solar flares than shorter-lived regions. NASA's report also says these long-lived regions are about 3 to 6 times more likely than other active regions to be the source of the most intense solar flares. That does not mean every long-lived region becomes dangerous. It means the odds look meaningfully different. The study focused on regions where strong magnetic fields take at least a month to decay. That matters because magnetic fields are central to flare activity. On the sun, magnetic structures store energy and can release it suddenly. The longer-lived regions may be telling us something important about how magnetic structures are organized and sustained. The report presents this as a strong indication that these regions are crucial for predicting space weather, and also potentially useful for understanding magnetic fields deeper inside the sun. One of the most interesting parts of this story is how the evidence was built. The study relied on NAS as solar active regions, Potter Citizen Science Project. Volunteers were shown pairs of active region images from NAS as Solar Dynamics Observatory and asked a series of questions about what they saw. Project leads Emily Mason of Predictive Science Inc. and Karen Easy, E.W. Ski of the Air Force Institute of Technology then examined both the data and the volunteer analysis. This is a useful reminder that large scientific image sets can benefit from many human eyes, especially when patterns unfold over time and across repeated observations. The project itself is now complete, but the results remains important. It suggests citizen science was not just a side activity here. It contributed to a finding with real forecasting implications. In a field where timing matters, better classification of solar regions can help improve how researchers prioritize attention and model future flare risk. The practical change is not that scientists can now predict every major flare. The change is narrower and more useful than that. If long-lived active regions are consistently more FLR prone, then forecasters may have a better early signal for where to focus. Instead of treating active regions as broadly similar, they can pay closer attention to lifespan as one part of risk. NASA's report says these regions are crucial for predicting space weather, which points to a forecasting gain. It also says they could provide critical information about magnetic fields deeper inside the sun. That second point matters because surface activity may reflect deeper processes we cannot observe directly in the same way. Still, this is not a claim that the problem is solved. It is a new clue, a strong one, according to the report, but it remains one clue among many in the larger challenge of understanding when solar magnetic energy will erupt. The careful reading here is important. The NASA report does not say long-lived active regions always produce the strongest flares. It says they are disproportionately active and several times more likely to be the source of the most intense events. That is a difference in probability, not certainty. It also does not claim a full explanation for why this happens. Instead, it points to long-lived regions as a promising window into deeper solar magnetism. So the honest takeaway is modest but valuable. We know more clearly which kinds of regions deserve extra attention. We also know that a citizen science project helped reveal that pattern. For viewers of this channel, the broader lesson is familiar science often moves forward not through a single dramatic answer, but through better sorting of risk, better categories, and better evidence. In this case, that means a clearer picture of which parts of the sun may deserve closer watch.